you can say the MMC is shown in the red. That means maximum diameter for the shaft is the MMC, whereas in case of hole, the minimum hole radius or minimum diameter is the max metal condition, because here the metal will from red to this outer boundary will be the metal. In case of the this will be the LMC. This the LMC least metal condition, this will be the size of the hole. That maximum size of the hole will be the LMC. Maximum size of the shaft is MMC. So you can see the metal allowed in this will be maximum if the hole size is minimum. So this is completely opposite to the shaft. I hope you are able to get it, MMC and LMC. So you can see over here, this is what the boundary shows the actual diameter. So for shaft, the maximum boundary would be the MMC. For this inner would be this LMC, and this will be the change in variation. Okay, so this indicates change in for the limits of size. Now second part would be actually this is limits of shape, actually not size. This is the mistake I have done. Limits for shape. So we can see the feature form. So the same diameter is given. We can see the LMC in the blue one and then MMC in the red one. But we'll say that by the size, the shape, that means the shaft, actual shaft is lies between the envelope of the given size, but the shape is board shape, just like a bow. You can see this is being tilted like a bow. So this is the shape is like a bow. This is vested. This you can see it is gradually coming. The black one shows the actual product, but by the size it ensures that it is within the envelope. But by the shape, you'll find this is bow shape. This is a vested shape. This is barrel shape, and this is the tapered shape. Here the taper is being shown over here. All ensures that it is within the size, but we'll find shape. Four different shapes has been shown in this. So which is whether this is allowable, because whatever the dimensions given over here, they only talk about the size. They don't talk about the shape. So this is dimensioning limits for the size. Now we have to check for this also, limits for the shape also. So what are the different shapes you can see over here? So parallel lines are there. You can use the parallel line, that means concentric circles. That means we are interested to find that the shape of whatever the product or shaft we have manufactured, it should be a concentric one. So parallel lines we require, parallel place we require, parallel place from the along the length, along the size, this is tapered one, parallel place here, parallel place over here also, and cylindrical zone here also. All this will make sure if all these are parallel, it indicates that they are talking about the shapes, not about the size. So you have to GD&T takes care of size as well as shapes. So we'll find the geometrical tolerance. Actually, there are 14 different geometrical tolerances and 5 different types of tolerance, geometrical tolerance, I would say. So they are actually categorized as 3 for individual features, for individual or related features, for related features. Now here, so this is total of 14. These are 1, 2, 3, 4, 5. So you might have seen when this GD&T is being shown, they say that GD&T is 14.5. Here indicating there are 14 types. Actually, characteristics are 14 and 5 types of tolerances are there. Form tolerances, profile tolerance, orientation tolerance, location tolerance, and runoff tolerance. So I will not talk much more about the geometrical tolerance much more. So I hope everybody have gone through it just for coming to the groom what we are will be doing in the actual model tools. Though we are doing the model tools, we are verifying these geometrical tolerances only. Geometrical as well as shape, size and shapes we are checking in the modern tools. So if you are using the whether you are using the CMMs or scanners, that does not make any sense. But what you are verifying is the what the tolerances has been specified by the design engineer with this help. That means he specifies in terms of variability. That means to understand the CMM, working of the CMM or working of the uh, scanner, one has to know the basics of this GDNT. So that is what that is why actually I was going through this geometrical terms initially so that you are comfortable at the end. Uh, so just for individual features form, so straightness, flatness, circularity, and cylindricity. We don't require any feature. That means we don't want to relate to anybody. It is self-sustained. That means straightness can be measured for a particular feature. You don't have to compare. So that means for comparison, we don't require anything. To this straightness, flatness, circularity, and cylindricity, we don't require any other feature to be compared with. For the profile of a line and profile of a surface, we may or we will not be. So this is actually for individual or related feature. Individual means we don't require any feature to be related. We have to compare. For this profile, actually we require or sometimes we don't require. So that depends upon how the profile of a line or profile of a surface is defined. But for related features, that means orientation, location, and runout. That means whether it is angularity, perpendicularity, parallelism, position, concentricity, symmetry, circular runout, or total runout. For all these, we require two features to compare. That means angle, one is 90 degrees, that means one surface is 30 degrees to other. That means we require two surfaces measured. That means they are related to each other. If perpendicularity also, one surface is perpendicular to other. Parallelism also, one surface is parallel to other. That means we require two surfaces, two related features to be related to each other. All these three, orientation, location, and runout, requires three different uh, two different surfaces or features to be compared with, whereas in case of for a form or individual feature, we require only single feature, we can check the tolerances. Okay, now in between the GNT will get some this important symbols one should know. Maximum material condition we already said, regardless of feature size, RS, what is the size it will do. Least material condition we already designed. Projected tolerance zone, diameter, this is phi, diameter or cylindrical tolerance zone or feature. Basic or exact dimension will be given like this. Datum feature symbol, datum is the surface from where we are measuring, the datum would be given by this particular symbol. Feature control frame, all these features would be given by this particular frame. This is called as feature control frame. So actually how it works. So you find feature control frame. The geometrical symbol would be shown over here. The tolerance information would be in second part. The datum references will be in last three parts. So datum is the reference. So reference may be 1, 2, or 3. So maximum would be a 3. So in some cases we may use only one reference. Sometimes it requires 2 or sometimes it requires 3. That depends upon which dimensions you are giving, which what we want to control. So actually two things are there. While specifying the this dimension, one has to look for what purpose this particular feature would be required in the assembly. What its function is, how it works. Accordingly, the dimension, these tolerances are given, and then if this is what this 3 shows. So this 1, 2, 3 required depending upon its function. So how it fits in the assembly, what is function. Accordingly, this value of all this means which size or how much size should be varied, how much shape should be varied, which is important, which is not, which is least important, which is more important. All this actually depends upon how the particular product or particular feature would be functioning in the assembly. So you can see how this is laid out. So you can see geometric country symbol, positioning. This is symbol for position. Phi 0.003, M is material condition, maximum material condition. This is your geometrical tolerance for the positioning. Then this is first is called as a primary datum. Second will be called a secondary datum, and third will be called as tertiary datum. So primary is this first will important, then second, then third. That means primary datum will be much more important. Then list will be the secondary, and then third will be the tertiary. Okay, so this is the position of a feature. What this indicates, the position of the feature must be within 0.003 diametral tolerance zone at the maximum material condition. This is the maximum condition relative to datums A, B, and C. So three datums have been shown. So with respect to this datums A, B, and C, datum means reference surface or reference feature from where you are measuring that particular distance. Okay, so all these three are there. This is how we read the control feature frame, and how the values are being specified depends upon what is the role of that particular feature in the assembly. Now, just we'll see the datums. So if you are not understood, just see, because this is important. Datums are features. It may be a point, it may be axis, or it may be a plane on the object that are used as the reference surfaces from which other measurements are made. So these are we call as a datum. So datums are three types: primary datum, secondary datum, and tertiary datum. So used in designing, so it is used for designing, tooling also, manufacturing also, inspection also, and assembly also. So you can see this is the references one has to. So what is given, which dimension has to be measured with respect to what datum, that will be given in GD&T. Okay, as you know, not every GD&T feature requires a datum. That is flatness, we don't require the datum. Okay, that means we already seen here that this four don't require the datum. This may require or may not require, and all this require the datum compulsory. Okay. Now here it is given, this base of this part is, this is datum A, this is datum B. Okay, so indicating this A surface. Now this surface should be parallel to A. Variation should be 0.005 with respect to A. And this says that whatever the angle is there with respect to B, so this angle is given 20 degrees, should only vary by 0.005 degrees, not more than that. So that means this angle will be vary with respect to this B datum. This is what, this is angularity, this parallelism. I hope you are able to understand the things. So this is how the datums are important over here. So just the placements of datums. The datum may be at the hole. So anywhere on this hole, the feature size such as holes. So the hole is a feature, or the surface is a feature. So that can be called as a datum. So you can see 5.5005 plus or minus 0.005. That can be varied with respect to this datum. Okay, so this feature, this also feature can be this called as a datum. We are talking about the placement of datum. Datum can be placed on the features used for the GD&T. Okay. The last basic things actually where we are will be looking at is degrees of freedom, because this is very important, because while specifying in the CMM also, as well as the coordinate measuring machine also, and the scanners. So which are, we say that which are the tools for the modern inspection, actually works on this 6 degrees of freedom, or tolerance itself actually works on 6 degrees of freedom. Sometimes in some literature, this 6 degrees of freedom is also called as 12 degrees of freedom. It's very simple. So we have 3 linear and 3 rotational degrees of freedom. Okay. Indirectly, what it says, so we have 3 linear. That means 3. If you see along x, y, z, so there will be the moment along the x, along the y, moment along the z would be linear moments. That means moment would be possible in 3 directions. So they are called 3 degrees of freedom, 3 linear degrees of freedom in x, y, and z direction. Or you can say here what they are saying, right, or left. So this is plus or minus in x direction, plus or minus in y direction means front or back, and then z will be up and down. So if you say it differently, then it becomes six linear motion. Instead of three, we say plus and minus. Plus means here, minus means there. Okay, so they become six linear. So in some literature, this is called a six linear, or in some literature, it's called a three linear. Three linear means plus x means towards the right, minus x means towards left, plus x plus y means front, minus y means back, plus z means up, minus z means down. That means x, y, z, three linear motion will give you the information where the change movement is being done. And three rotational means about rotation about, you can see here, rotation about x-axis, rotation about y-axis, rotation about the z-axis. So it is the rotation in clockwise direction, location in anti-clockwise direction. You can see here for this along the x-axis, that is right. This is in anti-clockwise direction. This is in clockwise direction. So that rotation will be along x, y, and z direction. That is clockwise and anti-clockwise. So that becomes if you see clockwise and anti-clockwise are separate, then becomes 6 degrees of freedom for rotational and 6 degrees for the linear. That means 6 and 6 becomes 12. That is plus minus if you say differently. If you combine it as single, that means plus or minus x, plus or minus y, plus or minus z, then becomes 3 linear, and then clockwise along x or anti-clockwise x axis, clockwise movement in y-axis, anti-clockwise about y, clockwise about z, clockwise about anti-clockwise about z. That becomes 3 and 3. So then we say 6 degrees of freedom. If we say plus or minus separately, then becomes 12 degrees of freedom. But you find this literature is different in that is this what I say degrees of freedom. Different literature says different things, 12 or 6, but it is the meaning is the same. What I was talking about datums, that is also important. So we say primary datum, you can see this for this particular object, the plane A, that is the bottom surface to the plane A, that is primary datum. The secondary datum, now you can see the secondary datum, this is your becomes your secondary datum, and tertiary datum becomes at this particular point. So all these three datums you'll find they will be perpendicular to each other. Okay. Now what is the how they are functionally defined? Because we have to define these three datums for the verification of tolerances. Okay. So primary datum is selected to provide functional relationships, accessibility, and repeatability. It ensures the functional relationships. So standardization of size is designed in the manufacturing of a part. Consideration of how parts are oriented to each other is very important. For example, Legos are made in a standard size in order to lock into place. Primary datum is chosen to refer the location of meeting surfaces. That means Legos means what we're talking about, the parts which are being joined. Generally the small size place that joining box, what we say, flying compasses, all these small parts they are talking about. So they are standard size. So they want to lock to each other. So you can see this this primary datums will come into this datums come into this. Accessibility, shafts get in the way. Whether shaft datum is required for the shaft, yes, we require the datums for the shafts. So what the primary datum review. So it is primary datum chosen must ensure precise measurements. Surface established must produce consistent measurements when producing many identical parts to meet required specified. That means repeatability, functional relationship, accessibility, and repeatability would be there for the primary datum. That means if we have to select, now it is not necessary that always this bottom will be a plane surface A, this would be the primary datum. You can call this vertical also primary datum, or you can call this as a primary datum, but in that case that should be an important basic point. We should ensure that it has a functional relationship defined with respect to that to all remaining parts. Here this is very easy because we can measure the height, we can measure its depth, we can measure its width very easily with respect to plane A, not with the others. Now with respect to this, very difficult to measure the how much is the height and all this thing. So we have to select the primary datum in such a way that it has a functional relationship, it should be accessible, and then it ensures the repeatability. Okay. So here you see the primary datum is shown. First datum established by 3 points. Minimum contact with simulated datum A. Now here, first datum established by 3 points. So you have to define 3 different points to define a plane. So you want the surface. So you have to mark 3 different points. That means 3 points reference point. I am talking about plane is defined. So this is very important. When a single point is there, it only indicates a single point. When we define 2 points, it defines actually a line. But when we define 3 different points on a plane, it actually 3 different points. This is what? This is single point. Okay, single point will show only point. 2 different points will ensure it is a line. Okay, and 3 different lines will ensure it becomes a plane. That means to define a plane A, we require to define 3 points on this surface. That is bottom surface of this plate. So if you see this as a plate as the your product, you have to define 3 different points on the plane. It ensures that these are the first step is established by 3 points. So you have to specify any 3 points on the bottom part of the plane. So that will be your plane number A. Okay. So that becomes your primary datum. Now for secondary datum, all dimension may not be capable of reference from the primary datum to ensure functional relationships, accessibility and repeatability. So when we are using the secondary datum, when you feel that all these 3 functions are not capable for the dimensioning or verifying the things, we have to define the secondary datum and as well as tertiary datum. So how you define the secondary datum? Secondary datums are produced perpendicular to the primary datum, so measurements can be referenced from them. So it sometimes becomes very easy to take the reference from the secondary datum. So we have to define the secondary datum such that it should be perpendicular to your first datum. This is how you can see plane B. This is plane A. This is the primary datum. Secondary datum is defined perpendicular to this. Okay. And tertiary datum again, the tertiary datum must be perpendicular to both primary and secondary datums, ensuring a fixed position from the 3 related parts. Okay. So that will be the tertiary datum. You can see over here we have defined the tertiary datum here. This is both perpendicular to this plane B and plane A. Plane A represents your primary datum, plane B represents your secondary datum, and plane C will represent your tertiary datum. Okay. Now here we are how to define the secondary datum. Okay. Now secondary datum, you see we have used 3 points on the surface of this product to define the plane. So 1, 2, 3 points are required to define the primary datum. But this is shown over by this particular symbol indicating this is the datum. The bottom surface is the datum, that is A. So A is the datum. So perpendicular to this on this line, that means on this surface is the B. So B is the datum. This is perpendicular to it. Okay. Now only so second datum plane established by 2 points contact with simulated datum 2 with simulated datum B. That means only 2 points are required to define this plane. Well, these 3 points are required. 1, 2, 3 are required to define plane A. Or in terms of, I would say, in terms of degrees of freedom, when you say we specify 3 points, we are locking 3 degrees of freedom in primary datum. When we specify 2 points on the plane B to define your secondary datum, we lock to 2 degrees of freedom, and only single is required in plane C, because third datum plane established by 1 point only. That means by just defining 1 point on the third surface, we require this plane C is defined. That means for plane A we require 3 points, for plane B we require 2 points, for plane C we require only 1 point, indirectly indicating 3 degrees of freedom are locked by plane A, 2 degrees of freedom are locked by plane B, and 1 degree of freedom is locked by plane A. So all 6 degrees of freedom are locked by the these three tertiary datums, ensuring that the whatever the product is there or whatever the manufactured part is there, it is fixed with reference to the system, and now you are ready to measure the size and shape for that. I hope this is the basic things one has to understand while doing the verification of while specifying the tolerance and while verification of the tolerance. Now, see, now till now when there was no free-form shapes. Now, just I would like to what is free-form shapes? Free-form shapes is a shapes parts are great interest in many applications such as aerospace. You can see the aerospace, the various wings are there. All the parts actually you find they are free-form. Free-form means they are not able to. We are not able to define by any particular equation. Suppose equation of a circle, parabola, we define this by particular equation. But free-form surface we are not able to define by any particular equation. You can see this curve on the turbines. So these are pumps. These are not defined by a particular equation. They don't have equation. So that all these surfaces, this is the blade of the turbine. This is the pump part or turbine part. This is the wings. We have different shapes of the part of the aeroplane, that's aerospace. All these parts are actually we call it the free-form shapes. These free-form shapes are not easy to specify. Now you can see what we are seeing over here. Very easy to, because these are shapes. This is a surface plate. So this is a plane surface. Very easy to define by the to specify the dimension, shape, size. We can specify very easily with the help of mathematical formulas. But very difficult to get this type of shapes. So for this actually, when this shapes comes into the picture, we have the limitations with our day-to-day inspection for the tolerances. For that, we actually require that is what modern metrology, we call computational metrology, which uses the CMMs as lasers for the verification of tolerances. So that means all these shapes. Question is why free-form shapes are coming into the picture. So require maybe functional. Now functional, the functional means here the tip of the plane will be very small. We call it as a nose. It has a particular shape. Now this shape is not for only it looks good or something like. It has function that it should have a limited friction. That means we can lift and drag. When it moves with a very high speed, the restriction, that means it should have a minimum the drag, or to say the force coming from the air should be minimum. So for that it is being streamlined. That's why the shape of the tip of the aeroplane will be like this, indicating this is not because it looks good, because this is functional, because it reduces the drag. Same thing, sometimes it is aesthetic, that just for it looks good. Some parts of the various parts of the various product is done smoothly, free-form surface, so that it looks good. Okay, so you can see the mouse also. Actually, it has the both functional and the aesthetic look. Ergonomics, now actually, all these three, aesthetic also and ergonomics also functional. Actually, all these are being defined in the this mouse. Ergonomically, shape should be such that it should be fit into your hand. Aesthetically, it should look good, and functionally, it will be easy to operate the buttons of the mouse. So the shape is made such that. So all this we call it as a complex shape, or we call it as a free-form shape. Now you see the designer tends to design the product of complex shape or free-form shape, because they are not only looks good, but they have some functions, or they ergonomically it has some particular reasons why they are made so. Now, it's not so easy to define this or to make specify the tolerances for this. So you can see what is free-form surfaces. For a product with a free-form surface, functionality of a surface is related to certain intrinsic parameters such as curvature. Now, functionality of the surface. The functionality of the, so we say the functionality of this turbine blade, or this one, or this, actually it is a functionality of related certain intrinsic means inside the body, intrinsic parameter that comes such as curvature. That means you can see all these things are defined by the curvature, which is the function of that shape itself within the body. So curvature is a property of the surface that is independent of the location of the surface in the space. So it does not depend upon the shape, does not depend on where this is placed. Shape is independent. We measure it as a curvature. How much is the curvature? How much is the radius at this particular point? How much is the radius of this particular point? That is how the curvature is made. Curvature is different at different points on the free-form surfaces. Okay, so designer would like to manipulate or modify design models by using parameters of features. So parameters, that means everything will be related to each other. A parameterization of free-form features is receiving much attention due to importance of this intrinsic product design. Now, what is the need and motivation for the tolerances regarding this product design, manufacturing and quality? Tolerance specification is primarily influenced by the product design, manufacturing process and metrological capabilities. So how the tolerance is important while specifying the tolerances. A general issue of tolerance is understanding the link between the functionality, geometry of the surface, ability to determine tolerances to provide the desired performance. So what tolerances should be provided so that it will give the desired performance, and then actually it is a link between functionality and the geometry of surface. This is the geometry of the surface. What is function? All these are related to each other. These tolerances are related to product design. It is based on the manufacturing methods and what quality you want. So this is, tolerance is not so easy. So all these things we have to take care. So you can see here the verification to be done by the particular advanced metrology. The manual inspection of parts with complex shapes is difficult and involves random and systematic error. So random errors will be there, systematic errors will be. Let's see the example over here. Now this is shape of any particular part. The deviation, allowable deviation is shown over here. Distances is 0.500 with each other. Now we have to verify. So in this case, it will be very difficult for the manual inspection. So it requires time also. Hence require the automation of the process. So that is why the manual inspection is replaced by the machine inspection. Machine inspection may be by CMM or maybe by the scan. Now see how this is done in CMM and scanner. That is data acquisition. How this is done? So data means information of the product. Now we use the vernier calipers or other micrometers by manual inspection. Various tools are there we use, but here we have to extract data from that means this is data will be a digital data. Out of whatever the data acquisition techniques we are talking about, it will be a digital data we acquire from the product, or we collect it from the product. So two methods are there: contact method and non-contact method. That means there is a contact of the stylus of the point with the material. That is the coordinate measuring machine is using the contact type of contact type for data acquisition. Non-contact, we have 3D scanners are being used. So three displays are laser, optical, and X-ray. But you find that actually in actual practice, X-ray has some problems which is actually uh, related to lens. So this is not much in the case for the 3D scanner. Optical has a problem that optical means light of photography, I would say. Just take a photograph and check the variation. This is can be used up to certain uh, time. But the problem with the optical is that it has some error. So when we go to the close tolerances, this can be not used for the close tolerances. That is the drawback of this optical type of 3D scanners. So majorly, generally, the scanners with the laser rays are being used as the 3D scanners and for the data acquisition. Data acquisition here means we are taking the various points. We are capturing the shape and size of the product of the product which is to be measured or verified for the tolerances. So coordinate measuring machine is the first. We'll be looking at contact type of data acquisition techniques. Second, we'll be looking at the non-contact type of data acquisition techniques. So these are the some various companies which are a big player in the coordinate measuring machine. So you might have heard the names of these, which is very good. Mitutoyo, Renisha, Verisub, all these, almost all are the big companies playing in the market. So generally, I would say the contact type of coordinate measuring machine generally looks like this. Okay, so it will move along. This is bridge. This is called the bridge type because this looks like a bridge. So it is capable of moving in X, moving in Y direction. This is X direction, moving in Y direction, moving in the Z direction. So this style, this part, actually we can see over here. Okay, so this can be rotated also along the axis, and then you can see this part actually shown over here. This is called the stylus. So CMM probe stylus for CMM machine tools, ceramic stem. This is ceramic stem, and then 6 mm. This is 6 mm. Ruby ball tips are used generally. So this is this is used ruby ball because this comes in contact with the product, ensuring that you have to make ensure that it is very delicate and it does not actually make strikes with the metal or other part. So if strikes with some force, it may break the some metals with metals or the glass materials or something like that. So we have to be very careful while doing this. So this is how the coordinate measuring works. So if you see over here, same thing is a bridge design. X means here they have defined X in this direction, Y in this direction, and Z in vertical direction. So this probe is we can move. This head can move in X direction. It can be this table can be this total thing can be moved in Y direction, and this can be lifted in vertical direction Z. Okay. Here we can see datum reference frame. So 3 frames are being shown. What I showed: primary datum, secondary datum, and tertiary datum. 3 points on this surface, 2 points on the second surface, and 1 point on this surface is sufficient to define your primary datum. This will be your secondary datum, and this will be your tertiary datum. The primary, secondary, and tertiary 3 datums are being used to specify the points over there. So the coordinate measuring machine is, you can see over parts with free-form surface are generally inspected by using the dedicated fixtures and coordinate measuring machines in an offline mode, not online mode, but in an offline mode. CMM uses contact measurement technique which has high accuracy, repeatability, and reliability. Contact measurement techniques are very slow in acquisition of data. This is important. This is their advantage. This is its disadvantage. Accuracy is very high. That means exact dimensions it can use. Repeatability means if you do number of times, it will do the same thing, and it shows the reliable things. Reliability is also good. So this is, but time is very less. It takes more time. That is the problem for to acquisition of data. Acquisition of data means, again I'm saying, collection of the important dimensions of object. That is nothing but your acquisition of data. So it is done taken in terms of x, y, z coordinator. So it comes whatever the coordinate touches. If this probe touches any particular corner, it measures the x, y, z coordinate of it. So just I will let you know how this is being done. So CMM measure and record x, y, z coordinates for each point measured. Which point is to be measured? All important points which you feel is important for the dimension has to be measured, creating a 3D point cloud that can be compared to a CAD drawing. 3D component means just like this. You can see here I show number of points has been taken from as a here as a single point. So 3D, this is 3D point because this is use x, y, z coordinate. So it is a 3D frame. So it is a 3D coordinate system, I will say. So this is called a 3D point, and this is called a cloud because number of points are there. So number of points are being measured. So this just seems to be it is a cloud of 3D points. So this is called as 3D cloud points. 3D cloud points or 3D point cloud. 3D cloud points or 3D point cloud, one is the same. Some literatures they call it 3D cloud point, or some literatures call it 3D point cloud, but it is the same. It is the cloud number of points which is acquired, measured by the measuring machine to that these points are actually compared with the CAD drawing. Okay, so CMMs come in many different shapes and sizes with varying levels of accuracy. CMMs are used to take precise measurements of a mechanical parts. CMMs can accurately measure features that would otherwise be difficult to characterize. Proper use of CMM requires understanding of DD&T. That's why I was talking about. That's why DD&T was important. That's why I gone through the minimum the basic types of the DD&T. Now, what are the different steps that for the CMM tactile program? Tactile means it touches the parts. So probe and stylus qualification, how to decide which probe and stylus to be taken care of, then how to align the things, this is important. And once then we do the inspection process, data fitting and verification, then measurement report design, measurement program test, measurement program revision and improvement. These are the steps in the CMM. So we'll just see with the probe and stylus what is probe and stylus qualification. The probe and stylus qualification are processed to precisely know the actual effective diameter of stylus tip. Now, stylus tip means I will go back to show. This is we say that this is 6 millimeter ruby ball is there. Whether it is exactly 6 or it is 6.001 or it is minus 0.001. Actually, how much it is, we have to verify. So we will call this as a effective diameter of stylus has to be recorded first with the given standard spheres. It has to be standard sphere will be given. Then we have to measure the standard sphere with the help of this stylus and the tip to exactly know how much is the exact dimension of this ruby ball is. Okay, and to know the orientation length of the stylus. How much is the length and orientation of the, how is length and the orientation. I was talking about what is the length of the stylus. Okay, exactly how much is the length and what is the orientation. So initially we have to fix this, then only we are ready to do the actual verification of the coordinate measuring machine. So this is the first thing we have to first step. Okay. The second one is alignment of the machine with the product. So alignment process is the process of transform the measurement coordinate system from the absolute coordinate system or machine coordinate system of CMM coordinate system. Okay. Now CMM, this has when it reaches 0, 0, 0, this is defined in the by the in the industry only, where this CMM is manufactured. So it has a defined value. We call it as a machine MCS or absolute coordinate system. Means a machine coordinate system or absolute coordinate system. ACS, absolute coordinate system or machine coordinate system. This is defined in the factory only, where this CMM is manufactured. So one cannot change this. Its lower limits of this would be your MCS. Now you have kept the product over here. Now you have to define your X, Y, and Z. So this is your X, this is your Y, and here we have Z defined at this particular corner. Now what is the relation between this point, that is MCS, and this is WCS? You have to define first. Now this position of this product to be verified is being fixed by the your primary datum, specifying the primary datum, secondary datum, and tertiary datum. You have fixed this position. After that, you have to find what is the relationship between MCS and WCS. Now, how much it varies by the angle, by the distances. So this will be very simple. It will vary in X direction, Y direction, and Z direction. The X, Y, and Z. So we know how much it varies. And then if we know this relation between this and this, then we can exactly relate all these corners, all these points with respect to this origin. So indirectly, this WCS becomes the origin for your product. Indirectly, this becomes 0, 0, 0 of a product, and this is 0, 0, 0 of a machine. So to find the relation between the two, once this is established, then we are ready to acquire the points on the product. Okay, so this is what this alignment means. Third is, this is how we can see the rest of the steps. I will special process. All these steps are being shown over here itself. So CMM will give some. These are the points. Black one shows the points which are gathered or acquired by the stylus of these coordinate measuring machines. This is the representation actually we get from various parts. Then this is geometry element. This is the geometry. This is maybe your the CAD geometry, and then actually we find the geometry verification. We are interested to find out the these holes and such things. So they will be compared. This both that means the points and the actual CAD model. They will be compared to find out how much is the variation in the this one. So number of points. Suppose for example, number of points on this surface. If you have taken 10 points, so 10 points would be fitted to form a plane. This plane would be compared with this plane. If you are taking the circular or cylinder, so all the points all along the hole on the cylindrical surface will be measured. That will form a cylindrical surface. This cylindrical surface will compare with the CAD model to verify, know whether how these surfaces are varying, how much it is varying. That can be compared. Okay. Now, what are the things associated with the coordinate measuring machine? Geometric complexity increases the number of points required to accurate measurements and hence requires more time. How is the geometric complexity of the product? That increases the number of points. So more the complex number, more points you require for the accurate measurement, is more time will be required. So this is directly proportional. More the geometric complexity, that means more the complex part, more time. Requires path planning for acquisition of points. This is important. It is not that we are doing one point here, then another point here. We know this plane is, if you define, so this is the first plane, this is the second plane, this is third, fourth, this is the fifth plane, then we'll go for this, then we'll go for this. All this has to be defined properly. This is called as path planning. So how the movement should be happen so that we require less time while moving from one point to another has to be done before we start. Okay. CMM contact to the surface of object may damage the object. This is important. So if a delicate part is there, just a glass part is there, so quite possible if contact is very hard, then it may break or damage the parts. So it has to be very careful while operating this. Flexibility of parts makes it very difficult to contact the surface with touch probe without creating an indentation. that detects the accuracy of the measurement. So this is the one more drawback. If parts are flexible, so they will deform. If they deform, then indentation would be created. Indentation is created, then actually it detracts from the accuracy. So this is again the drawbacks of the coordinate measuring machine, that if the part is flexible enough, so it very difficult to get the how would say exact location or exact accuracy will be get reduced for the flexible parts. But it produces the traceable data. Traceable data means it understands what is. This is very important. This is very important for the coordinate measuring machine. It knows that now when we are already defined the path planning, so it knows traceable data means we know beforehand that this is the particular point from where this is being acquired. That means if you get thousands of points as a cloud data, each point belongs to which surface, that is traceable. We can find out its traceability. That means this thousand points are being also collected by the same. It knows from where it is being collected. That is important part. That is the important aspect of the coordinate measuring machine. Okay. So this was the part of the coordinate measuring machine. So in later part, we will go to the second part, that is 3D scanner. This is also called as non-contact type of scanner. There is no contact between the measuring machine and the product. So you can see over here, the camera is there, laser is there. This lasers are being pointed on the target object. You can see the XYZ is defined. Turntable, it will rotate on the turntable, and all this shape will be recorded in the form of cloud data. Now here in CMM, we have only collected thousands of data. Here we say lakhs and millions of data is being acquired by the laser. So data here would be very high. Number of points will be very large in numbers would be there in case of laser scanner. Good number of points would be there. So the accuracy of this is much more than the CMM. So, but in some cases, what I would say, the traceable points, that is the problem with the scanners actually. I would say to see how it actually works. You can see the actually camera holder. So it just scans by the plane by plane. So how much is the width that is defined? It just will go and scanning all the points like this, and it will collect millions of points. So 3D scanners capture the geometry of physical objects with thousands or millions of measurements in no time. But important drawback of non-contact system are they do not provide traceable dimensional metrology. Traceable, that was the actually the important feature of measuring machine. Whatever the data which you have taken, they know from which point actually which data is there. But here we get millions of points, but we don't know actually this point belongs to which. If you have the data, just I will show this. These are the 3-point cloud. So you can see some one object is there. Here this cup is there. This torus is there. Some building is there. Now actually this is not a building. Actually this is the cloud of points. They are very close to each other, but we don't know actually this tip of a particular tip is there, or the surface is there. Actually, this point belongs to this or this or this or this, which is very close to each other. So that traceability is not maintained in the point cloud data. Okay, again I am repeating, traceability is not maintained in the point cloud data in case of 3D scanner, whereas we have the traceability in case of coordinate measuring machine. So this is the basic difference between the scanners and the coordinate measuring machine. But rest of the procedure now. Just we have talked about acquisition of data. So acquisition of data is only different. Rest of the things is same. That means once we do these two processes, rest of these three, all the parts are same in CMM as well as in laser scanners. So acquisition of data is only change. Acquisition is contact type in CMM, non-contact is Kale, the scanner. We get first a point of data. Now, what is the difference? CMM enables track the correspondence between the nominal and manufactured surface for tolerance verification, that is traceable geometry is possible. To respond the market quickly, it has become inevitable to use 3D scanners to scan an object with multiple unorganized points as an input in online or offline mode. Uh, so that means which actually this shows the time required is very less in case of scanners. So, but important drawback of non-contact is that they are traceable geometry is not used. They don't have the traceable dimensional geometry for the. So, as the correspondence is maintained in the data acquisition by CMM, it is possible to measure deviation of a corresponding points on a manufactured feature or surface and CAD model using CMS only and not using the scanners. So, that was actually what I was talking about. Now, this is rest of the part which we will be discussing. Now, this would be the same in case of CMM as well as in case of laser. So, this is called as a computer-aided tolerance verification process. Now, we have the 3D CAD model. That means this ideal model is there with us. Acquired 3D data, that means whether it is by CMM or it is by the scanner, that data would be there. They computationally they will be aligned. That means they will be aligned properly to each other. Okay. Then verification between the two would be done, and then deviation will be shown. So that means the rest of this process would be the same. So you can see the import CAD model, that is 3D CAD model, import points, that is your acquired points from the CMM or maybe from the scanners. So you'll find they are aligned. You can see this and these two are aligned. Almost they are overlapping each other. And then deviation, you can find they are showing the deviation. You can see over here the deviation is more showing in the red. So that is the deviation actually between the two data sets. This is how this is done. Now this is again this alignment. It's not so easy. We have to take a lot of care while doing this. We are going to learn that how this is being aligned to each other. Okay. So alignment, acquisition of data complex part we are done. Multiple view acquired 3D data we are done. Filtration of noise from data. That means number of points would be added in the while doing this, whether it is not in the CMM, but in case of scanners, you will find noise will be there. Noise means unwanted data will be there. So we have to filter it out. So this is the first step which is taken care. Now, so many algorithms are there to filter out the data. That means, suppose if you are talking about the plane, so all these points will lie within the plane. So all this plane will form a single. All these points will form a single plane. But offset from this, a single point is there, offset from this plane. So you indicate the single point. It cannot be a single point. That means this is a noise. So such algorithms are there in the software itself. So that actually detects the this noise from the data. So that forms the plane. Okay, that's from the plane, or we call this filtration of noise from this. Now, once this is done, then it's called the registration is happening. Registration or alignment. So the another word for the registration would be alignment also. So alignment is done of the data points. Then it's segmented. That means segmented means segmentation would be means the data. Suppose we take all this data points for. Okay, I will take example of this one. So all the segmentation is this one plane. This is one segment. For this plane, this is second segment. At the top would be third segment. Either surface will another segment. Such type of segmentation of data is done. That means segmentation means we are just cutting down separating the data, 3D points. The surface fitting. Surface fitting means whatever the segmentation is being done for suppose for the inner surface data is being segmented out, surface is fitted for the inner surfaces, and then it is being checked. Okay, now uh, inspection frame, CAD reference frame, and then this is being aligned. Now you can see over here, CAD reference frame is this is the from the 3D geometry. This is the actually curved points. Inspection reference frame. This is the third point. So major point set is obtained with respect to the inspection reference frame. So we know the point set of this. Nominal CAD model is defined in CAD reference. This is CAD reference. This is nominal, means your ideal one. So an important step in the verification process is the localization of IRF with respect to CRF. This is called localization, or it is also called as registration. So it is one of the same. So in some cases we say it is called the registration, or in some cases it is called the localization. So I may use the words localization as well as registration, but it is the same. That means what indirectly we are defining what is how to fix this frame with this frame. Okay, so the goal of localization is to find the transformation that optimally positions the major points set in CRM. That means now we want to align this part with this. Now it is not that take these two parts and align. So you have to make sure that suppose we are talking about this particular corner should exactly join with this particular corner. Now this is not a single corner. This is number of point clouds are there. Here also number. This is your 3D model. So this corner, once it is being surface fitted. Surface means because points will be there. From points we will create a surface to all the points. Crowd of points would be there all along this surface. We'll fit the surface, and that looks like this. So this point has to be coincide with this particular surface. So you can see. So this is how we call. So we have to find out the transfer, how to move this to this. So it is not only the movement. You have to move all 6 degrees of freedom. You have to lock out. That means we may move by 3 degrees for 3 rotations and 3 linear motions has to be compared. Has to be done so that exactly it matches with this. So for that we have to define which is the best 3 different points for XY. We have to define this CRF and IRF. Okay, so you can see over are aligned in this figure. Now how this is correspond for this localization. Now this process I will explain this process now how this is localization takes place. So correspondence for localization. In case of specified datum plane, a correspondence is established by fixing a datum plane in the major data and transformations applied to complete localization. That means one surface datum plane is fixed. Okay, so this is the datum. This is the points. From this points, we'll form a plane over here. From this plane, we'll take 1, 2, 3 points. This is best fitted to form a single plane. So this plane is moved to the in a such a way that it coincides with the your CAD model. Okay, so this is called correspondence for localization. For models without datum planes, localization is done in 2 steps: initial post estimation and solution refinement. That means without datum planes, because in some cases their datums are very different. Then also we can do the correspondence can be done. So in approximate solution, distance is minimized between the CAD model and point data by using the least mean square distance considering the entire CAD model and point cloud. So the distance between the 2 points should be minimized. So it is oriented. So this is oriented such that distance between 2 points. Now this is the distance. Now if it is not aligned, we will find this is the distance between these two. This is the distance between this. This is the distance between this. So we have to align such that distances between the corresponding points should be minimum. That is called as, this is nothing but your this is called as a least mean square distance for least mean square distance thus in the enter CAD model and point plotted. So in solution refinement, the distance is further reduced by applying iterative closest point ICP algorithm for point fixed by establishing a correspondence based on geometry. We have to first define the corresponding between the geometry. That means actually IRFS here has to be defined first, and then how what transformation has to be applied. We have to take a decision on that. Okay, so the corresponding points are decided by choosing the closest point, minimize the distances, corresponding points are represented, and they should be coincide. Once this is done, the closest point is stable for the matching of surfaces, but not the tolerance verification process when the tolerances are prescribed. This is closest point we can do when there is no datum. Okay, so we have to use different algorithms when tolerance verification for the tolerance verification when datums are prescribed. When datums are prescribed, means actually what we are doing XYZ defined here XYZ of the point cloud data. This is matched with this, and then movement three linear not sorry angular movement between these two reference frames has to be transformation has to be done, and then it will fix on its own. Okay, now are you getting more? Sir, we have the time with us. Hello. Hello.
Hello, sir.
Can I continue?
Yes, sir. Yes, sir.
Okay. Now just see the just I will just go through the profile tables, which is the need of an hour, because this is where the metrology, that means computational metrology will come into the picture. Profile tolerance. Here, profile tolerance, I have already said, it is very difficult where we use the CMM and lasers for this. So the current art, actually, this is we call this as a non-uniform tolerance. As you can see, the tolerance is different at this particular point. This is different at this particular point. This is different at here. This is much more closer here, and again, this is even more closer. Actually, this is actually this is not same across this curvature. This is called non-uniform tolerance is there. So very difficult to find the location, because it is a function of location of the surface. So difficult to verify. Even in 14.5, that is in 2009, this is not defined. The non-uniform tolerance is not defined. So we can only define the uniform tolerances, but does not support the, so current state of art tolerance does not support the non-uniform tolerance verification which is being done in 2009. So actually, what is the problem with this? If this is the case, actually this is manufactured surface A, B is a nominal surface, that is the CAD model, and B is your manufacturer model. So actually what is expected, this 2 is the distance between the two, suppose. So this is shorter distance method, that ICP method, what they call it. But if we align this like this, the distance between, this is the corresponding point A and the corresponding B, actual distance is 2.48. Okay, so it measures the minimum distance. If this is the minimum distance, it will measure 1.80 only, but the corresponding distance is 2.48. So this will be accepted. Actually, this is out of it is not within the tolerance zone. So this should be rejected. But now the this is being accepted. That is the problem with the scanners. So this can be done with the help of middle axis transform math, using the math, which gives the correspondence between the one point to another point that is missing in the current one. So that is what this would be. Okay, thank you. So if you have any questions from your end, actually I have so many slides further also, but I feel that okay, this is enough for you today. Thank you very much for your patience listening. If you have any questions from your end, you are free to ask them.
Any questions from participants? Any questions? Uh,
I think there are no questions from the audience.
oh, yes, yes, sir. So, thank you, sir. Thank you very much for accepting our invitation and giving your valuable time from your busy schedule. Sir, really,
Thank you.
today's yes, sir. Today's topic was really innovative and nice, and this knowledge will be very helpful to all our participants. And all participants will percolate this knowledge to their students as well. So, sir, once again, thank you and thank you very much.
Okay, thank you one and all for your patience listening. Thank you.
Okay, sir, thank you. So, participants, next afternoon session will be start at 2:30 p.m. Okay, thank you very much.